Good day everyone. In this presentation, we will discuss experiment 10, which focuses on the convex lens and how to determine its focal length experimentally. The main goal of this experiment is to understand how parallel light rays behave when passing through a converging lens, and how we can measure the focal length using different methods. We will go through 3 approaches, compare their accuracy, and finally focus on the most precise method, which is the displacement method. We will compare 3 methods: quick estimate, lens equation, and displacement method. Parallel rays converge at a focal point, and the distance to it is the focal length. This slide outlines the progression of methods used in the experiment. The first method is the quick estimate, which is simple but not very accurate. The second method uses the standard lens equation, which improves accuracy but still has some limitations. Finally, the displacement method is introduced, which is more advanced and provides the highest precision by minimizing measurement errors. In the quick estimate method, we use a distant object as the light source. Since the object is very far away, the incoming rays are nearly parallel. The lens focuses these rays onto a screen. By adjusting the screen until a sharp image is formed, the distance between the lens and the screen is approximately equal to the focal length. In this method, we use the lens equation. We place the object and screen on opposite sides of the lens and adjust the system until a clear image is formed. We define u as the distance between the object and the lens, v as the distance between the lens and the image. Then we use the equation 1 over f equals 1 over u plus 1 over versus. By measuring u and v, we can calculate the focal length f. To improve accuracy, we repeat the measurements. For each trial, we adjust the positions to obtain a sharp image, then record u and versus. After that, we calculate the focal length for each trial and take the average value. Repeating the experiment helps reduce random errors and improves the reliability of the results. In the displacement method, we fix the distance between the object and the screen, which we call x. This distance must be greater than 4 times the focal length. Under this condition, there are 2 different positions of the lens that produce a sharp image. We label these positions as L1 and L2. Instead of measuring from the lens center, we measure the displacement between these 2 positions. The focal length is calculated using the formula f equals x squared minus d squared, divided by 4x. Here, x is the distance between the object and the screen, and d is the distance between the 2 lens positions. This method is more accurate because it depends on relative measurements, which cancel out systematic errors. To perform this method, first, fix the distance x between the object and the screen. Second, move the lens until a sharp image is formed and record its position as L1. Third, move the lens again to find the second sharp image and record L2. Then calculate d as L2 minus L1. Finally, substitute the values into the formula to find the focal length. This slide summarizes how accuracy improves across the methods. We start with a simple visual estimation. Then we move to a mathematical calculation using the lens equation. Finally, we use the displacement method, which avoids errors related to the lens center and provides the most reliable result. This table is used to record experimental data. We write down x, L1, L2, and calculate d. Then we compute x squared minus d squared and use it to find the focal length. It is important to record all values carefully and maintain consistent units throughout the calculations. The displacement equation can be rewritten in a linear form. X squared minus d squared equals 4f times x. This can be expressed as y equals m times x, where the slope m equals 4f. This allows us to analyze the data using a graph. In the final step, we plot the graph. We place x on the horizontal axis and x squared minus d squared on the vertical axis. The data should form a straight line. The slope of this line equals 4f, so we can determine the focal length by dividing the slope by 4. This graphical method provides a highly accurate result based on multiple data points.